of section 1.2 from the OpenStax PreCalculus book. In this section, you're going to learn more about domain and range. Specifically, if I give you a function like f of x equals x plus 3 divided by x minus 1, what is the domain of this function? That's one question that I'm going to answer. To figure that out, the way I like to think about it is there's these things called domain rules. And really, they're what you cannot do. This helps you figure out what numbers are not in the domain of a function. So, for example, you might be asked down here, this is f of x. You might be asked to find the domain of f. And the way I like to do it is I like to think about what's not in the domain. So the way I'll figure out what's not in the domain is the things that are not in the domain are the things that might make me divide by 0, or the things that make me take the square root of a negative number. And really, I'm not being very precise there. It's not just the square root, the 4th root, the 6th root, the 8th root. Any even root will cause trouble if it's a negative number in there. Those are not the only two things that can go wrong, but for our purposes, for now, they're the two that can go wrong. Later on, you'll learn about logarithmic functions that have domain restrictions and inverse trig functions, but all that's a ways away. So for now, we just got to worry about these two. So here's some examples illustrating that. If my function is x plus 3 divided by x minus 1, I can put numbers like 4 into this function, and it would be whatever 4 plus 3 is, 7, divided by whatever 4 minus 1 is, 3. So put 4 in, 7/3 comes out. Okay, cool. You can put in a lot of different numbers, but there's one number that you cannot put in, and you might be able to just look at this and tell what number you could not be able to put in. I'm going to talk through it a little bit. First of all, note that there's no square roots or 4th roots or 6th roots or any of that going on down here, so I don't have to worry about my second domain rule. Really, all I got to worry about is make sure I don't divide by 0. So what number would make me divide by 0? Again, you might be able to just look at it and figure it out, but maybe you can imagine a harder example where you couldn't just look at it and figure it out. So a method for solving this is I want to figure out what will make me divide by 0. Here's the denominator x minus 1 from this function. If I set that equal to 0 and solve this equation, what I will be doing is figuring out what values of x make the bottom here 0. In other words, what numbers are not in my domain. So this is a pretty simple equation to solve. I get that x equals 1. So this is the number that is not in my domain. Oh, that's kind of weird. If they asked me to find what numbers were not in my domain, I could just say 1. That would be easy. But it doesn't. It asks me to say what numbers are in my domain. So my answer is, I don't know, the rest of them. So now we need a way to be able to write when our answers involve infinitely many numbers, like everything but 1 would involve. And so first, a pictorial representation of this answer. I want everything except for positive 1. In a picture, that's this right here. Turns out there's two different ways you can write these set of numbers. One's called interval notation, and the way you'd write that would be something like this. What this is saying is I want all the numbers from negative infinity up to positive 1, but not including positive 1, which is why I have the parentheses here, not a bracket. And then I also want all the numbers from 1 up to infinity. This right here represents this picture right here is what's called interval notation. Another way you could write this set is what's called set builder notation. These squiggly brackets mean the set of all. So the way I would say this answer is it's the set of all x such that my value of x is not equal to 1. Could write it like that. I don't like that. Another way I could express this set is with what's called set builder notation. Same basic idea. I have these two different intervals, the left side and the right side. On the left side, I want the set of all x such that x is less than 1. The squiggly brackets, the way you say that mathematically is the set of all. The vertical line here is how you say such that. So it's the set of all x such that x is less than 1. But that's not everything, that's just this half of it. So you're like, oh, put the u in there for union. Actually, no, you write the word or when we're dealing in set builder notation. I say the set of all x such that x is greater than 1. This is the right-hand side here. This is equivalent. This one's called set builder. This one's called interval notation. Either way are ways you could state your answer to this problem. Maybe a little bit quicker down here. Here I have to take into account both of my rules. I can't take the square root of a negative number. So this thing underneath the square root sign, that 3 plus x, better be greater than 0. Right? In order for it to not be negative, I guess not greater than, but greater than or equal to 0. The thing underneath the square root sign, which is what's called the radicand, needs to not be negative. The way you can mathematically say not be negative is say it's greater than or equal to 0. So now I got to solve this equation. I guess I could subtract 3 from both sides of the equation and get x is greater than or equal to negative 3. But that's not everything. This is part of my domain. This is one restriction on my domain. But I also have to make sure I don't divide by 0. Well, what numbers will make you divide by 0? You could stare at this thing for a while and try to figure out the solutions, but it's a little bit tricky. You might be able to figure out that 1 would be something that would make the denominator equal to 0 and therefore something I don't want in my domain. But if you follow the blueprint from above, what you do is you take the bottom, the denominator, and set it equal to 0 and solve. And the way you solve this equation is by factoring. This is factoring a quadratic with the leading coefficient equal to 1. I'm assuming you know how to do that. If you don't, maybe I'll make a video on it or something. This factors as this, and so this tells you that either x minus 2 equals 0 or x plus 1 equals 0. Therefore, either x equals 2 or x equals negative 1. So okay, now you got to make sense of all this work I just did. I'm saying to be in the domain, x has to be greater than or equal to negative 3. However, things that are not in my domain is 2 and negative 1. So I kind of start out with everything greater than negative 3. I better draw a picture. Here's my number line. Here's negative 3. Here's negative 1. Here's 0. And here's 2. Not drawn to scale, but that's all right. And I want everything greater than or equal to negative 3, so I'm going to include this point. But wait, make sure you don't include negative 1, which I just did. Make sure you do not include this point here. And make sure you also do not include this point right here. So really I'm talking about that interval, this interval, and this interval. Damn, so 3 different intervals. So if I'm writing this in interval notation, I would say it's everything from negative 3 up to negative 1, including negative 3 because this circle is closed, but not including negative 1. Union, everything from negative 1 up to 2, not including either of those 2 endpoints because both the circles are open. And then union everything from 2 to infinity. Not including infinity because it's not a number, you never include infinities. That's how you'd write this in interval notation. You could also write it in set builder notation. You could say it's the set of all x such that my value of x is between negative 3 and negative 1. Note that I have less than or equal to here, but just less than here. And that's because I do want to include negative 3, but I do not want to include negative 1. And then I'll say or the set of all x such that, and now I want my x to be in between negative 1 and positive 2, and I don't want to include either of those 2 endpoints, so I'd write it like this. And then finally, the set of all x such that x is strictly greater than 2, not greater than or equals 2, because I don't want to include 2. 2 different ways you could write this same thing. There's some examples on how you find the domain. There's an easier way to find domain, not going to lie. However, it's dependent upon you having the graph of the function. If you have the graph of the function, not only can you figure out the domain, but also the range. Later on, we'll learn a way to figure out the range of a function when you have it written like this without graphing it. But for now, that's beyond what we can do. All we can do is find domain. So one of them, probably the main learning objective, is to figure out the domain of something like this and something like this. Apply these 2 domain rules. A second learning objective is what if you have the graph of a function? So I got to come up with the graph of a function. I'm going to kill 2 birds with 1 because it's supposed to be the fast summary. I'm going to graph this piecewise function, which is my final learning objective, and then use the graph of that to show you how you can figure out the domain and the range of a function if you have the graph. So a piecewise function. This is all just one machine. It's just this machine does different stuff depending on what input you give it. So if you give it a number less than negative 2, it's kicking out that same number. If you give it a number between negative 2 and 1, it's going to square that number and then kick that out. And if you give it a number greater than 1, it's giving you the output 3 no matter what the hell you give it. You give it 100, it gives you 3. You give it 5, it gives you 3. You give it pi, it gives you 3. Anyways, how would you graph that? Well, if you have those toolkit functions from the previous section memorized, you'd know that a function h of x equals x is just the kind of diagonal line graph. But I don't want to draw the entire diagonal line. I only want to go to an x-coordinate of negative 2 and below. So I'm going to say it looks something like this. Hard to draw on a computer. It's supposed to be a straight diagonal line. Note the open circle because I do not want to use this rule when x is equal to negative 2. I'd want to use this next rule. And this next rule corresponds with the quadratic graph. And you may remember that the quadratic graph looks something like, again, hard to draw on a computer, but I'm going to call that pretty damn good. There's this U-shaped graph. It's what's called a parabola. And note that I don't want to draw the entire parabola. I just want to draw it from negative 2 up to positive 1. I want to include the point at negative 2, but I do not want to include the point at positive 1. And then finally, I want a height of 3 anywhere that x is greater than 1. So if I'm greater than 1, not equal to 1, but greater than 1, I want a height of 3. I guess that doesn't need to be all squiggly like that. Let's just draw a straight line. It's just hard to see because my pen's in green and the graph is also in green, but whatever, I think you can figure it out. So this entire thing is one graph. I know it jumps, but that's okay. This whole thing is one graph H. When I have the graph of a function, I can figure out its domain and its range. And the way you do it is by kind of thinking back to what domain means. Domain are all the numbers you can put into the function. It's all the possible x values. It's all the x values that have a height associated with them. We can go back and look at the graph. Which x values have a height associated with them? You might say all x values. You'd be wrong. You'd be like, oh, right, -2 doesn't because this circle's open. No, actually, you're wrong again. -2 does have one. It's just way the hell up here. So which one doesn't? 1 does not. There is no output defined for 1. For any other x value, there's a defined output. So what I want to write in either set builder or interval notation is all numbers except for +1. I'm a fan of interval notation, so I'm going to write this in interval notation. I'm going to say it's everything from -infinity to 1, union everything from 1 to infinity. That feels familiar. I think I did that over here. Range, there's something we haven't talked about at all. The range is all possible outputs. The outputs are graphed on the y-axis. So when you're asked what is the range of a function, you're being asked what heights does your function have? So now instead of looking at the x-coordinates, all possible x-coordinates, you're looking at the y-coordinates. You're trying to figure out what y-coordinates have a height associated with them. Maybe I should switch colors here. I just messed up range. Now you can't even read that, but at least you can hear me. The range is the y-coordinates. Looks like I have y-coordinates all down here, and then it picks back up here and goes all the way up to here. Any y-coordinate in this range, or in either of these two intervals, would be in my range. So I want all of the numbers from -infinity all the way up to -2. I do not want to include -2 because this height never comes out of my function. And then I want to pick back up at 0 because I can get a height out at 0. I want that to be a bracket, not a parenthesis. And then I want it to go all the way up to 4. You're like, what about this part at 3? Really, you don't even have to worry about that because I was already getting an output of 3 over here. So that really doesn't affect anything in terms of my range. I want to go from 0 up to 4. I want to include 4 because this circle right here is closed. This would be my domain. This would be my range. Graphically, you can think about your range as all possible y values and your domain as all possible x values, which I suppose I could draw like that. You're like, wait, why is this not an open circle here? Again, it's because of this closed circle here. I think that's everything you need to know about, or at least the short summary of everything from section 1.2, so I'll stop this video here.